Well, welcome everyone to another TCS Plus talk. So this week we have Renato Ferreira Pinto Jr. From the University of Waterloo, who's going to tell us some very exciting work about directed isoperimetry and monotonicity testing. I think this will be a paper presented at Fox in a few weeks, so you can see it here in TCS Plus. But before that, just before we get started, I just want to say that TCS Plus is an online TCS seminar. It's been going on now for over 10 years, and we're always looking for suggestions from our viewers or for people who organize TCS Plus. So if you see interesting paper that you think would make a great TCS Plus talk, please send us the suggestion on our website. And before we begin, I also wanted to thank the rest of the organizers. This includes Clement Canon, Rachel Cummings, Emily Fox, Sumega Garg, Yasmin Nazari, and Shivam Nadimpali. And with that, I guess I'll hand the floor over to Renato and please take it away.
Thank you very much, Eric, for the introduction, and also thanks everyone from TCS Plus organizers for inviting me and everyone who is here. So yeah, let's get started. This talk is about this connection between directed isoperimetry, which is something in the realm of mathematical analysis, perhaps, and monotonicity testing, which is this algorithmic problem. And I really want to emphasize kind of how these two meet and why this is interesting and tells us something new about both analytical results and perhaps more relevant here, the algorithmic results. So let's get started with the first half of this connection, which is the isoperimetry part. In particular, I want to tell you a little bit about Poincaré inequalities and why they are very important. They're very natural, show up everywhere, and we should be kind of interested and excited about them. So Poincaré inequality is a type of local to global inequality. So in particular, to be concrete here, let's fix some nice domain omega in Euclidean space, which I'm representing with this blob here. And then there's some exponent p that doesn't matter too much. And then let's let f be some smooth enough real valued function whose mean I'm denoting by f omega. Then a Poincaré inequality says something like the following, that the LP distance, the LP norm of this difference, f minus its average, is at most proportional, at most some constant times this norm of the gradient of this function. Okay, so the way to interpret this is that the left-hand side is something like the distance to a constant function. So here I'm just writing out what the LP norm is, and we're saying how far is this function from being constant everywhere in its domain. On the right-hand side, so yeah, so this is like a global property. On the right-hand side, what I have is what I'm calling here local violations. So some sort of like local property. And why I'm calling it a violation is because, well, this gradient is non-zero when the function is, non-constant locally. It's varying a little bit. And that is like violating the property of being a constant function. So this is this type of local to global phenomenon. Okay, so Poincaré inequalities have a very long history. So it started with Poincaré himself in 1890 in the context of studying partial differential equations for mathematical physics. And in particular, as he observed, it turns out that inequalities of this type instantiated with the exponent p being 2, um, if you study that inequality, then the constant c, the best constant c that you can get, characterizes the exponential convergence of something called the heat equation. So this is something that is relevant in physics, and we'll get back to that in this talk. There are also other connections. This inequality with p equals 1 characterizes something called the isoperimetric constant. And in the discrete world, this connects to expander graphs and Chigurh inequalities and spectral graph theory and things like that. And there are many more connections in mathematical physics, as I mentioned, in geometry and probability theory, concentration inequalities, diffusion processes, many things. So, so that was the first part of the title. So now let's move on to the second part of the title, which is monotonicity testing. And in particular, I wanna start by telling what property testing is. The algorithmic component of this talk will be about property testing problem. So property testing is the following type of problem. We have some universe X of objects and some property P, which is a subset that we care about. And we want to design an algorithm which distinguishes whether this object is indeed in P, so this object X has the property we care about, or not only does it not have the property, but it is epsilon far from having the property. So pictorially, P here, this gray area denotes the objects we want to accept for sure. And then anything that is epsilon far from this area, we want to reject for sure. And if it's in between, then maybe we'll accept, maybe we'll reject. We don't care. And the reason why we give ourselves this epsilon room is because we want to make this decision without looking at the entire object X. We want to make just a few queries to it. So we want to minimize our query complexity. And this requires us to make this sort of approximate decision. Okay, so that's property testing. And this work studies the particular problem of monotonicity testing, which is a central classic problem in property testing. So the property of monotonicity is the following. We have some partially ordered domain, which I will make concrete in a second. And then the function f is called monotone if whenever x is below y in this order, f of x has to be at most f of y, so it cannot go down. So this is really a very classic problem in property testing, has been studied for over 2 decades in many, many settings. Perhaps the most classic setting and the one arguably we know the most about is the fully Boolean case, where f takes inputs in the Boolean hypercube and outputs a Boolean value. So this was studied initially by a series of papers by Godrai, Godwasser, Lemon-Ron, Sofiaras Hoinkavas, master's thesis, and then also Dodis and Saburnitsky. And there have been many, many more works and breakthroughs ever since. These early works, they actually studied even a more general version of this problem, where your domain can be the hypergrid, not only the hypercube. So now you have the discrete line from 1 to n in d dimensions. And perhaps your function can be real valued as well. So this has been studied, and there are also recent works in this setting. You can go beyond that and study general discrete posets, so partially ordered domains in general. This is a pretty challenging setting, but we have a little bit of work there as well. You could also go beyond the discrete setting and study the continuous setting. So perhaps your domain now is the continuous solid cube from 0 to 1 in d dimensions, and your function may be arbitrarily real valued. And in particular, this is the setting that I will be looking at in this talk. And for the most part, I am going to be talking about upper bounds, and that's what these citations are for the most part as well. But there are also many works on lower bounds. And we understand some of these settings better than others, but there's also a lot of interesting works on lower bounds. For this discussion, to keep the content focused, I'm mostly going to be talking about the Boolean case as our kind of gold standard for comparison, and then the continuous setting, which is what this work is exploring. Okay. And by the way, feel free to interrupt with questions if you have any at any point. So, okay, before I jump into the concrete results of this paper, let's do a warm-up. And the purpose of this warm-up is to convince you that isoperimetry, this notion of isoperimetry, first explain what it is, and second, why it's relevant to monotonicity testing. So let's consider the fully Boolean case that I was talking about, and then consider maybe the most natural tester that you might guess if you first start to study this problem, which is the following tester. You sample a uniformly random edge from x to y. So that means that to obtain y, you simply take x and you flip one of its bits from 0 to 1. And then you check if that edge violates monotonicity. That is, if f of x is greater than f of y. If it is, then you reject. And you repeat this test sufficiently many times. This is called the edge tester. And the question is how many times you need to repeat this procedure in order to succeed with probability at least, say, 2/3. That means that if f is far from monotone, then you will indeed reject. If f is monotone, then this will never reject because every edge satisfies monotonicity. So to answer this question, we have this classic lemma from those earlier works that I was mentioning, which places a lower bound on the number of violating edges. So what the lemma says is that if this function f is epsilon far from monotone, and if you write v of f for this number of violating edges, then v of f is at least this quantity epsilon times 2 to the d. Okay, so that's the lemma. What does that tell us about a success probability? Well, the success probability or the rejection probability of the tester is going to be the number of violating edges, epsilon times 2 to the d, divided by the total number of edges, which is d times 2 to the d, because every vertex in a hypercube has degree d. So this is roughly epsilon over d, and therefore d over epsilon queries suffice. And that is the classic edge tester result. Okay, so we're happy. And the claim to start motivating this talk here is that there's a Poincaré inequality hiding in this lemma. So that's the first example of a connection between isoperimetry, Poincaré inequalities, and monotonicity testing. So let me show you why that is the case. Okay, so I'm repeating the statement of the lemma here. And recall what I was telling you in the first slide is that Poincaré inequalities have the form that looks like this. F minus this average, taking the LP norm, is at most some norm about the gradient of F. Okay, so let me write this a little bit differently. Essentially equivalently up to some constant factor, I'm going to rewrite this left-hand side. Instead of talking about distance to this average function, I'm just going to write distance to a constant function. So that's the notation here that I'm going to make more concrete in a couple of slides. Distance to a constant function in LP norm, don't worry about the P too much, is at most. And then here I'm just explicitly writing out an expectation for this LP norm. Again, it's just like some notation choice. So the distance to a constant function is at most this expected norm of the gradient. Okay, this is the Poincaré inequality in general. Now I want to claim that this Boolean case is hiding a Poincaré inequality, so I need to tell you at least what this gradient is going to mean in the Boolean case. So I'm going to write gradient of f in this Boolean case for the discrete gradient, which I obtain as follows. Here in this picture, I'm going to choose a point x, for example, this one on the lower left. And then the discrete gradient is going to be a vector of length d, so one entry for each dimension. And then for each dimension, I'm going to take the directed edge, and I'm going to take the difference between where the edge points, its destination, minus the source, the value of f there. So here the first coordinate is 1 minus 0, which is 1. The second coordinate is also 1 minus 0, which is 1. So that's the discrete gradient of f at x. For this point y up here, now if I look at the first dimension, the horizontal edge, then I'm going to have 0 minus 1. I always look at the edge in this directed way. So 0 minus 1 is minus 1. And indeed, this is a violating edge. It violates monotonicity. And then in the second dimension, again, I have 1 minus 0. So that's 1 here. So that's my discrete gradient. And then I'm also going to introduce this notation, gradient minus, for the directed gradient, which is simply the minimum with 0. That means that anything that is positive, I just zero out. And I only keep the negative entries, which are precisely the entries corresponding to violating edges. Okay, so if I do that, then this lemma here, by dividing by 2 to the d on both sides and then flipping the inequality, is equivalent to saying the following. On this right-hand side here from the lemma, I'm going to have epsilon, which is my distance to monotonicity, in particular in L1 norm. So I'm saying here that the L1 distance to monotonicity of f is at most, well, if I take the violating edges and divide by 2 to the d, what I have is an average degree. And I'm going to write the average degree in this way here, is the expectation over the vertices of this L1 norm of the vector that I just told you is measuring the violating edges. Okay, so the lemma is giving us this inequality. And if you compare this inequality to the Poincaré inequality that I just gave you, there's something about the exponent p that you have to choose, but the most salient modifications or changes are two. First is that instead of measuring distance to a constant function, we're measuring distance to a monotone function. And second is that instead of having this gradient, the usual gradient, we have a directed gradient. So we make this choice on the left-hand side, this choice on the right-hand side, and I'm claiming that this is a directed version of the Poincaré inequality, a directed Poincaré inequality. So that's the first hint of a connection between monotonicity and Poincaré inequalities. And now I want to convince you that the connection goes much further, and forgive me for one slide with a little bit of definitions here. So here's the language that I need to talk about this connection a little bit more deeply. So there's going to be some P and Q, which are exponents about how to take LP norms and the norms of vectors that we are taking. Don't worry too much about it. P and Q are just some reasonable fixed numbers. And I'm going to say that the classical Poincaré inequality in this LP LQ world is something like what I just told you about. Distance to constant is at most the norm of the gradient. And then I have the appropriate exponents and norm indices here. And then I'm going to say that a directed Poincaré inequality is the same thing, but now I'm measuring the distance to monotone functions. And then I'm going to take the directed gradient on the right-hand side, so only those negative entries. And then here to be explicit, when I say distance to constant, I mean the minimum distance to any constant function in the appropriate space. And distance to monotonicity means the minimum distance to any monotone function. And the conceptual way to think about these inequalities is that, as I said in the beginning, they are a connection between local violations and distance to the property of interest. So here, local violations of monotonicity and distance to monotone functions, and the same for the classical inequalities. All right, so with this language in place, I'm going to use this map here to do two things. First, convince you that this connection between isoperimetry and monotonicity is very intriguing and very rich. And second, by showing you this landscape, I want to convince you I want to help you understand where this particular paper that I'm presenting is placed and why it helps us understand this landscape. So the way to read this map is here the columns in blue. On the left, I have a discrete column where I'm only talking about Boolean world. And on the right-hand side, I have the continuous world where I'm talking about this continuous setting in the solid cube with real valued functions. In terms of the rows, the bottom row is the classical world. So here, there's nothing to do with monotonicity. It's like classical isoperimetry, like discrete geometry or mathematical physics um, works. And then on the top row, I have the directed version of these things. So these are the ones that have something to do with monotonicity and that we have learned about in the past decade or two. So okay, if I start to fill in this map here, in the discrete world, for Boolean functions, the most classical type of Poincaré inequality for Boolean functions is this L2O2 that is called the Poincaré inequality on the hypercube, if you look at analysis of Boolean functions texts. And it turns out, I'm not going to spend too much time going over details, but it turns out that this, for Boolean functions, also implies this L1 inequality, so just the exponents work out. And the point here is that once I have this L1 classical inequality, I can not derive, I can compare it to an L1 directed Poincaré inequality. And this is the inequality that I just told you about. The dilemma could be rephrased as the directed Poincaré inequality. So this is the edge tester inequality. And we just saw that this implies the edge tester with big O of D query complexity. So this is our first connection from some classical Poincaré to some algorithmic result. This connection goes much further. There's an inequality that is not in Poincaré form, but something that is isoperimetric in the classical Boolean world called Margulis inequality. And it turns out that this implies this implied the first tester with sublinear query complexity in the Boolean case. And this was by this breakthrough work of Deeparnav Chakrabarty and Seshadri. And they were the ones to first observe this connection that I'm telling you about. So this connection is really due to their observation. And they used it to get this first sublinear tester. So that's great. If you go even further, there's an even stronger classical inequality by Talleyrand. This is Talleyrand's inequality, and it turns out that you can phrase it as this L1, L2 Poincaré inequality. And from that starting point, can we have a directed analog? The answer is that yes, we do have one. And in fact, this other breakthrough work of Kotman and Safra showed that a directed version of this L1, L2 Poincaré inequality gives you this tester with square root D query complexity with a lot more technical work to obtain it, but you get this square root D tester, which is optimal for non-adaptive testers. So this is like a really impressive result. So okay, this connection is very rich in the discrete world. Now what happens in the continuous world? The point is that, as I was telling you about, Poincaré inequalities, isoperimetry in general, are very well understood in the continuous world as well. They really started with the study of mathematical physics, which is like starkly continuous. And so what I want to claim to you here is that if the connection between classical indirected isoperimetry and monotonicity testing is really fundamental and has some sort of underlying principle behind it, then it's natural to expect that it also holds in the other setting where classical isoperimetry is really well understood and really important. So I want to understand the rest of this map. And if I want to understand the rest of this map, the first observation I can make is that starting with this L1 inequality from which I got my first kind of equivalence or my first connection here, there is an L1 inequality in the classical world as well. The easiest way to get it is by some like fancier inequality by Bubkov and Houdray. So we're kind of taking some advanced results and getting something basic out of it. But okay, we can get this classical inequality. And then there is a directed analog of this inequality. This is something that I showed in a paper last year, at random 2023. And this gives you a O of D tester in the continuous setting. So this is somehow the equivalent of the edge tester in the discrete world, but now in the continuous world. So we obtained our first connection. We started this program also in the continuous setting. Things seem to be working. Now, two things are kind of missing here, or are the obvious next steps. One is that I told you we started with this like fancy inequality and again got this L1 inequality that gave us something comparable to the edge tester. But we have not yet explored the most well understood, the most classical Poincaré inequality in general, and especially certainly so in the continuous setting, which is this L2 inequality, the same one that I told you was classical in the discrete case. This is the one that you can prove by Fourier analysis, is the one that Poincaré himself studied. This is a very classical object. So it should imply something about monotonicity if this connection is really fundamental. And the second thing is that I haven't told you anything about sublinear testers. And given the developments in the discrete case, it seems like we want a sublinear tester here too. And these two questions are what this work is exploring. Okay. So in this talk, I'm going to tell you about an L2 directed inequality corresponding to the classical one here. And I'm going to show you that it implies a tester with square root D query complexity. Okay, so we get something sublinear. And in fact, for the type of tester that I'm going to tell you about, square root D is optimal. And let
So
me just, yep.
you're probably gonna say this soon, but what is the parameter m here going to correspond to?
Yes, I should have said that I will tell you soon. So this M turns out to be a Lipschitz constant. In the real valued setting, we need to assume something. And then for this work, I'm assuming a Lipschitz condition. Um, so yeah, I'm going to tell you more about, but it's a Lipschitz constant of F. Okay, so yeah, so that's the map, and then where this work is placed. And let me just say that at least conceptually similar results also hold for the hypergrid and for real value functions on the Boolean cube. So this connection goes even further. Maybe the notation needs to change a little bit to accommodate like a more general notion. But for now, let's keep the discussion focused. Okay, so what are the goals of this talk? I want to do three things. The first one is to give you an idea of this square root D tester. Why does it follow from that directed Poincaré inequality that I just announced? At least to get an intuition for what the tester is doing, how it's using the inequality. And then in terms of proving the inequality itself, which is the bulk of the paper, I don't want to make it too technical, but I would like you to have like two takeaway ideas from it. The first is this idea of a directed heat equation, which is this partial differential equation, this PDE that I study in the paper to get the inequality. And I want to just give you a notion of why studying a PDE makes sense if you care about algorithms. And then the second one is this particular technical ingredient in the proof, which is a detour through optimal transport, which proved to be a really interesting, useful way to tensorize an inequality. So I had an inequality in one dimension, and now I want it in d dimensions without losing any factor of d. And it turns out that optimal transport seems to have a natural, seems to be a natural tool for tensorization. So I'd like to tell you a little bit about that too. So before I can tell you about the testing result, I need to give you the model and also answer the question about M as well. So let me give you the testing model. Uh, you need to choose the model a little bit more carefully when it comes to testing real valued functions, but it turns out that this has been done for us. So we're going to adopt the LP testing model initiated by Berman, Raskolnikova, and Yaroslavtsev. Okay. And the regularity assumption that we're going to assume, because for real value functions, you have to assume something, maybe bounded range, maybe some Lipschitz condition, maybe you can assume something else. But we're going to assume that the input function is Lipschitz. And just to tell you, this is the same as the previous paper that I mentioned from 2023 of my own. So our input is an M Lipschitz function where M is some fixed parameter in D dimensions. And we want the tester to accept if F is monotone and reject if it's at least epsilon far from monotonicity in this L2 distance. And what is our access to F like? So the most usual type of oracle access to a function is a value oracle, where you can give a point x and you obtain back f of x. Now, it is much more convenient for this talk, for this paper, to assume the following oracle. I'm calling it a directional derivative oracle. So the way this oracle works is that I give it a point x in a direction v, so v is a vector, and it tells me back the directional derivative of f at point x in direction v. So this is the inner product or the dot product between the vector v and the gradient. I don't want to spend too much time on the model, but let me tell you two things about this. First, if f is reasonably smooth, in particular if it has bounded second derivatives, you can simulate this directional derivative oracle using value queries. And second, I'm not assuming that I get the entire gradient of f for free. I'm only getting it in one direction. So these two observations are just to tell you if you think this is like scary or too strong. I would argue it's not. It's actually comparable to the value query, and it's not like d times more information or anything like that. Okay, and then the prior work in this setting, as I told you, was a tester with linear query complexity in D. And the main question that was left open is, can you do sublinear? So now I can tell you the results. And it comes in two parts. So the first part of the result is this directed Poincaré inequality. So we show that for all functions in the sufficient regularity class, don't worry too much about it. We have this L2 directed Poincaré inequality. So L2 distance to monotonicity of f, and it's convenient to square it on both sides, is at most this expected squared norm of the directed gradient. Okay, so this is the inequality that I promised you on the map. And what does it imply for monotonicity testing? So it implies that in the model that I just showed you, there exists a tester that is non-adaptive, uses directional derivative queries. It's an L2 tester, as I was telling you about. It accepts M Lipschitz functions, and its query complexity is up to a log factor in D, is square root D M squared over epsilon squared. And by the way, don't worry too much about this, but if you're interested, you should think of M and epsilon as trading off with each other because you can rescale the entire input. So this is the right shape in some sense. And let me just tell you, without going into more details, that for the class of tester that we're looking at, which is essentially equivalent to the pair testers in the discrete world, this query D is optimal. So that's not a general lower bound, but it tells you that if you want to do better, then you need a different type of tester than what we have.
Can I ask a question?
Yeah, for sure.
So just to understand, so does this result imply the Boolean monotonicity tester?
That's
Oh,
a great, yeah, so that's a great question. It is open for, it's an open question that I propose as well. It does not readily imply that. I still have hope that maybe we can get something, but it would require work. Is not a, I don't think there's a black box implication. I think that's like a very interesting follow-up question.
so just to understand what breaks down, because as in this seems to be a superset of the problem, and the function is smooth, or isn't it? Are
Yeah,
you
so I guess what breaks down is a few things. We have this, so it depends on, like if you wanted to do a reduction and you had what you have with you is a Boolean input, and then you want to run this tester, simulate this tester, then this tester is going to look for points inside the solid cube. And if, you maybe could try interpolating like your Boolean input to get a function that fills the entire cube, but then each of those points depends on like exponentially many points. So you could try sampling to get an approximation, but you got to worry about the accuracy that you need, and you got to worry about the Lipschitz constant that is implied by a Boolean function on the cube. And it turns out that if you just try to work the parameters through, you need too much precision, you need too much accuracy. So I think you need to do like maybe like a gray box reduction where you actually like you can compare the gradients of the smooth function with the discrete gradients of the Boolean function, and it seems like you can get something. But to derive something like the path tester, it seems like there are some ingredients missing, so it's not obvious for me yet.
thinking?
Yeah. Okay, so this is the result, and let me start by giving you an idea of what this tester does, and then I'll give you an intuition, not a foolproof, but an intuition for why this tester works if you assume the Poincaré inequality. So the tester works as follows. It is going to simply sample a uniform point x in the solid cube, and then it's going to choose this direction v for the directional derivative query according to some distribution d that I'm going to tell you about. But importantly, this direction is going to be all positive, like it's going to point only up in every dimension or zero. And then we're going to reject if the directional derivative in that direction v, so if this inner product is negative. And again, this is never going to reject a monotone function because this directional derivative is always going to be at least zero. So our task is to show that if f is far from monotone, then we're going to witness one of these negative derivatives with some reasonable probability. And to argue this, I use this lemma, which I'm calling detecting negative entries with subset sums. And as the name suggests, the idea is that our direction v here, we have a lot of freedom for how to choose v, but actually we're going to be much more restrictive, and we're just going to choose v to be subsets of the coordinates. So it'll just be Boolean vectors. And then the claim is that you can choose some distribution over these Boolean vectors such that we have the following statement. So think of u here as the gradients of a function f at a certain point. And then what I'm saying is that this inner product is going to be negative with at least this fraction. And let's parse this fraction. So first of all, on the numerator, we have the negative entries of u and then the sum of those squares. So think of this as the total weight in some squared sense, total weight of the negative entries. And then I'm dividing by the total weight of all the entries of u. So this is somehow the relevance, the relative weight of the negative components of u compared to all of u. And I would like, to have the probability of success, probability of detecting that u has some negative entries, be growing as that grows. And this is what this lemma shows, but we incur a square root d loss. Okay? So we incur a square root d loss, but not a d loss. So that's the key point here. And one way to think about this lemma is that it's if you're familiar with a group testing problem, which is where you have a large population and you want to test a large group all at once and hope that you will detect some problem in the group, then this is a similar kind of thing, but we have a signed version because you can have positive entries and negative entries, and we want to detect the fact that it has negative entries. So let me first take this lemma for granted and then tell you why it implies the monotonicity testing result. So here's why that works. Let's compute the rejection probability of this tester, okay, when f is far from monotone, epsilon far. So the rejection probability is going to be the average over all the points x of the probability when I choose v that I detect this negative inner product, okay? So first I'm going to apply my lemma. So this is going to be the average again over x of this right-hand side here, this fraction. So I have the negative gradient on the numerator, the usual gradient on the denominator, and then I have this loss square root d log d. Now I'm going to use my Lipschitz assumption. So the denominator here, this squared gradient is at most m squared. So I'm going to pull out 1 over square root d log d m squared. And then in the numerator, I just have this total expectation of the directed gradient. Now I'm going to use my Poincaré inequality to say that that is at least my square distance monotonicity. And by assumption, that is at least epsilon squared. So my probability of rejection is this epsilon squared over m squared square root d. And that's what gives me the query complexity of roughly square root d. So assuming the lemma, this is why the tester works. Now, I don't want to prove this lemma to you because it's not technical, but it has like a bunch of calculations. But I want to give you an intuition for like why you might expect this lemma to be true enough that you would just try to prove it yourself, perhaps. So let me try to prove this to you, or like to convince you that this may be true. For simplicity, let's assume that these square weights on the numerator and denominator are roughly some constant. Maybe they're between 1/2 and 2 or something like that. So we're not going to worry about these values. Let's just assume that this is roughly balanced. It's a big simplification, but still. Now our task is to detect that U has some negative entries. And I'm going to break it down into two very extreme cases, just again for intuition's sake. In the first case, suppose that I have more than square root d entries that are negative, that are in the support of the negative part of U. Well, in that case, I'm kind of done, because if I guess my vector v to be a singleton that only picks a random vi to be 1, then with probability at least 1 over square root d, I'm gonna pick a negative entry, and then this inner product is gonna be negative. So I'm done. That distribution works. Now let's look at the opposite example, the opposite extreme, where there's only a single negative entry in U, so the support of the negative entries is 1. And then by my assumption, this is going to be something like -1. And then let's assume that the rest of the mass of U is uniformly divided along all the other entries. So all the other entries are going to be roughly positive 1 over square root d. So the sum of the squares is still 1. Okay, so if that's the case, then it turns out that if I guess V as a random subset of size roughly square root d, then this should also work. Because if I take square root d elements and if they don't touch the negative entry, then I'm not gonna detect anything. I'm not gonna win. But if I touch the negative entry, then that's going to contribute negative square root d, and my positive entries are going to, it's going to contribute -1, and then my positive entries are going to contribute roughly +1, and if I balance the constants appropriately, that distribution is going to work. So these extreme examples kind of work, and then to interpolate between these extreme cases, it turns out that it suffices to guess this size of v, the number of entries in v, as this exponential doubling sequence, 1, 2, 4, 8, up to d. So I have log d possibilities, and that's where the log d comes from here. And then I kind of argue about the thresholds in this vector u, and I find a granularity that works. That's roughly how this lemma works. And then I conclude the tester. Okay. So I don't want to tell you too much about the tester anymore. I will just make one observation related to the question about the Boolean world, which is if you're familiar with the path tester from that KMS 18 paper that I told you about, then our tester is essentially the continuous analog of the path tester. In the path tester, I choose a length to the decay for a path, and then I take edges at random, a random walk. Here, I'm choosing a length to the decay to be the number of entries in my vector v, in my directional derivative query. and then choosing the edge I in the path tester seems to be equivalent to choosing direction I in my directional derivative query. So there is a conceptual connection here, but I don't know about a formal connection, and I will leave that as an open question for the end. But that's all I want to say. Now with the algorithm part covered, let me tell you a little bit, give you a little bit of intuition for how the proof of the Poincaré inequality goes, and talk about those two ingredients that I told you to give you a flavor and the main takeaways, in my opinion, from this proof. So for that, let me start by telling you about the heat equation, which is the PDE that really inspires this work. So the heat equation has the following form. Fix this solid cube domain, and then let U be a function that depends both on time t and on the position x, and think of U as the temperature at that point, okay? At that point in time and in space. Then the heat equation says the following, that the way that this temperature is changing over time, this derivative with respect to time, is going to be equal to this Laplacian, which is the sum of the second derivatives of U in space. Okay, we actually don't care too much about this multidimensional version. So let me tell you that when we're in one dimension only, then this is the form that it takes. The dt of U is the double derivative in x, dx dx of U. Okay. Now I wanna give you some more intuition for this equation, but before that, I can actually just show you an animation so that it'll be more concrete. So here's a short animation for the progress of the heat equation. So the graph here in red is the value of U at time 0. And this is what happens if you let it run. It just converges to the average temperature over time, okay? So the regions that are too hot to go colder, the regions that are too cold grow hotter. So this is what the equation does. And here I have a pictorial view of it. And one thing I wanna just hint at this point is that this inner derivative dx of U here, you should think of it as the flux or the momentum or like the flow of particles at a certain point. So another way to put it is that there are two ways to view this PDE. One, which is more immediate perhaps, is this value view, where you look at a certain fixed point of the function and see how it's changing over time. So this point is going to be increasing over time. This point is going to be decreasing over time. But here I'm switching things around and thinking about this particle view, where instead I look at each point as like the concentration of particles, like the graph shows you the density of particles at that point. And then I'm thinking of these particles as moving in order to fill this valley, and then kind of like moving off of this hill and filling this valley. So the particles here on the left are moving right, the particles here on the right are moving left, and the result is the animation that you saw. So this is the heat equation. Now, why is the heat equation interesting connected to the Poincaré inequality? Well, one fact is that it turns out that the Poincaré inequality, as I said in the beginning, characterizes how fast this converges, in particular, the exponential convergence of this process in the following sense. It turns out that the variance of this function U, which somehow characterizes how far from equilibrium it is, it decreases exponentially at some rate c, if and only if a Poincaré inequality holds with constant, say, 2 over c. Okay, so there's an intimate connection between these things. There's another way you can measure the progress of this PDE other than the variance, and this is by this notion of energy called the Dirichlet energy. And the way that you compute the Dirichlet energy, the way that you define it, is by taking the integral or the average over the entire domain of this quantity here, this squared derivative at a given point. And I want to say this is the sum of the local violations of the function. Again, this derivative is non-zero when f is non-constant. And it turns out that the Poincaré inequality also implies that this version of energy decays exponentially over time as you go towards equilibrium temperature. And this is going to be critical for us. So now I want to carry this connection over to the director world to claim that the same principle holds and give us the monotonicity result. So for that, I need a new PDE. I need a PDE that will converge not to the average temperature, but to some monotone function. And then I want to study how this progress occurs. So here's the PDE that I propose, and I'm calling this the directed heat equation. It looks almost the same as the usual heat equation, the classical one, but this inner derivative here, I'm taking this minus, which means the negative component, minimum with 0. So the way to think about this is that when this inner derivative is negative, meaning that the function is decreasing at a point, this will behave exactly the same as the heat equation, and it will tend to make the decreasing region into a constant region. So that's good. It's fixing violations of monotonicity. On the other hand, when this inner derivative is positive, meaning the function is already monotone, then this will be zero. So the function, the PDE is static there, is not changing the function at all because there's nothing to fix. Okay? So this is a picture of like the particle view of the directed heat equation. So I only have these particles on the left rolling off towards the valley, and I expect it to converge to this monotone function in red here. Okay? And let me show you an animation for that. I guess a video is worth continuously many words. Okay, so this is the progress of the directed heat equation. If I go back, you notice that this increasing region is kind of frozen in time, but then it's slowly fixing all the violations and pushing more and more mass to the right until I just have this flat region and then whatever monotone region remained. Okay, so this is my equilibrium as I had expected. So because this converges to monotone limit, what I hope by analogy is to learn something about distance to monotonicity. And I'm going to analyze it via a directed version of the Dirichlet energy that I just told you about. So I'm going to define the directed Dirichlet energy to be just the integral of now the local violations of monotonicity, so the negative parts only of the derivatives in x, and then squaring everything. Okay, so do we have this exponential decay? Does this program work out? It turns out that yes, if you study this PDE, you can conclude this. The main technical tool to study this PDE is something called gradient flows and also something called maximum monotone operators. So these are well-known tools in the world of nonlinear PDE. And I'll just tell you, it's not that trivial. It turns out that this PDE is like highly, highly nonlinear. So even if you look up like nonlinear PDE theorems, none of them are going to apply essentially because this nonlinearity is very, very stark. And usually in nonlinear PDE, people try to work with like bounded nonlinearities in some sense. But it turns out that because this PDE is like very principled and like natural and like there seems to be like a strong reason why it should behave that way, you can with enough work show that it still works. But you need a lot of technical lemmas and that's why if you've looked at the paper, it has way too many pages. But this program works. So that's all I want to tell you about the PDE. Now, okay, we've concluded exponential decay of the energy. Where does that take us? Why is that useful? Before we get to a Poincaré inequality, it turns out that there's something more natural that the PDE tells us about. So we're going to derive that first. And that's an inequality in optimal transport space. So there's a very intimate connection between PDEs and optimal transport. Let me tell you why. So the main concept in optimal transport is this Wasserstein distance, which is the distance between measures. And in particular, this squared Wasserstein distance, informally, between measures row 0 and row 1, is the minimum cost that you can achieve to go from row 0 to row 1 by moving mass from one to the other, where moving mass from some point x to some point y costs the squared Euclidean distance between x and y. Okay, so imagine that you're just moving the mass to try to get to your destination, but you're going to pay squared distance cost each time. And the reason why, well, you should expect this to be connected to PDEs because PDEs are all about, locally shifting those particles around, as I was telling you. And it turns out that you can make this concrete. So there's something called the Benamou-Peñier formula, which tells you the following. This is the big formula here, but it tells you the following. If you can come up with some sort of velocity field that describes how those particles are moving to reach row 1 from row 0, okay, so you have some sort of plan for how fast the particles got to move, then if you take the integral of the total value of this velocity field, so you should think of this as some sort of total kinetic energy, then that is an upper bound for the Wasserstein distance because I'm giving you one way to move the particles. So it turns out that if you take the very best of these plans, then that is exactly equal to the Wasserstein distance. And the reason why this is useful for us is because this velocity field here, well, velocity for us, it turns out, like you can make this concrete, is roughly the same as momentum, which is roughly the same as flux. And flux is what I was telling you about. There was the inner derivative here in the heat equation that tells you how fast the particles are moving at a given point. And the total flux is precisely the Dirichlet energy. So, and this thing is decaying exponentially. So if this energy is small and is decaying exponentially, then in total, this integrated quantity for these velocities is going to be small. So I expect my Wasserstein distance to be small. And that's exactly what we show. We combine exponential decay with Benamou-Peñier, and we show this transport energy inequality, which says the following. If I take this function u, and I just transform it into a measure in mu by just making u the density of the measure, then the Wasserstein distance from mu to that monotone equilibrium, the final version of the animation that I showed you, the monotone function, is going to be at most this energy functional, which is precisely these local violations integrated. So if the violations are small, then I'm close to monotone in Wasserstein space. Okay, so was it useful to get this transport energy inequality? I'm going to claim yes, and the reason is because it's going to help us move from one dimension to d dimensions, to tensorize. And how are we going to do that? The answer is that we're just going to do this one coordinate at a time. We're going to fix our domain, our hypercube, our solid hypercube. We're going to run the process in all the rows, then all the columns, then all the third coordinate, and so on. And the reason why this is going to give us a tensorized inequality is simply because of the Pythagorean theorem. So in this picture here, if my domain is just a square, my first step, if I have some mass particle here, is to run the PDE along the rows, and that's going to give me some horizontal transport bound. And then the second step is going to run it along the vertical axis. So I'm going to get some vertical transport. But recall the Wasserstein distance squared is just measuring squared Euclidean distance. So if I compose these transport plans, I'm going to get this diagonal movement, and everything's going to add up perfectly by Pythagorean theorem. So if I make this formal, then what I can get is this tensorized inequality, where for a multidimensional function f, the square Wasserstein distance from the initial state to the final state where everything is monotone because I've fixed all the coordinates is at most now the square norms of the gradients of the directed gradients, which is exactly what I want in my right-hand side. I'm writing integral here instead of expectation, but it's the same thing. So this is exactly the right-hand side I want in my Poincaré inequality. And the only thing I'm missing is that I have Wasserstein distance here instead of LP distance, which is what I wanted. So I don't want to give you too many technical details because I think it's not the main point of the paper here, but it turns out that these transport energy inequalities are very, very closely connected to Poincaré inequalities. And in fact, the connection goes further. Transport energy, Poincaré, Telegram inequalities, log Sobolev, these things have many, many implications and equivalences depending on the particular setting. And in particular, this kind of transport energy inequality that I just showed you and Poincaré inequalities are essentially equivalent in the classical setting. So our only job is to get something back in the directed setting. And it turns out that we can. We can get at least a directed implication. So what we can prove is that if this directed transport energy inequality, which is a thing that I derived in the previous slide from the PDE, if this holds, then I can obtain a directed Poincaré inequality, where essentially the left-hand side replaces Wasserstein distance with L2 square distance. And this is exactly what I wanted to show. This is the Poincaré inequality that powers this theorem. So this works. And all I want to say here in terms of technical ingredients is that it uses duality. And basically the one most important tool in optimal transport is this notion of Cantor-Lewicz duality. And that's exactly what we use. And the proof is not too different from the proof of the classical equivalence. You need new technical tools or technical lemmas to handle the fact that everything here is directed, but it would be the natural thing to try, essentially. So that concludes what I wanted to say about the paper itself. And for some concluding thoughts and open questions here, the main theme of this work is that we were interested in extending this connection between directed isoperimetry and monotonicity testing. And in particular, one takeaway here is that this connection is really, really robust to the choice between discrete and continuous settings. So even if at a moment we don't have an implication between the two, it's interesting that, you know, the ideas, it really does seem like there's a fundamental connection that is robust even to the choice of setting here. And in particular, the fact that we got this square root D tester seems to help unite what we know about continuous world with what we know about discrete world. And as far as takeaways for perhaps like taking this to other directions in other works, I would say one is the fact that the convergence properties of this PDE is the principle that is underlying both the classical and the directed phenomenon. And the fact that to tensorize this inequality, tensorization is something that, you know, is challenging in general. It like gives us trouble everywhere. Optimal transport seemed to come to the rescue. Maybe it can help elsewhere. So that's why I wanted to kind of advertise it here. And in terms of open questions, I will say, first of all, as was already raised, can we get a reduction or implication for the Boolean case, especially considering that our tester seems to be the continuous analog of the path tester in the Boolean case? Can we make this formal? I've tried a little bit. You can get something, but I don't know for sure. And then another point connected to the first actually is can we get lower bounds for this general continuous setting without assumptions about the tester, just lower bound for general testers? I don't know how to show good lower bounds for this problem. And then the third kind of open-ended direction is, can we take these tools elsewhere in property testing or even in TCS? As I said, optimal transport seemed to come in very handy for tensorization. PDEs could be a natural way to compare objects when they're more continuous. And maybe to be concrete, one problem where perhaps this could apply is convexity testing. But for now, this is just thought I haven't really tried very hard. So that's all I wanted to say. And for one concluding advertisement, I am looking for postdocs for next year. So if that sounds relevant, please feel free to reach out. But thanks a lot for your attention.
Okay. I guess we can open the floor up for a few questions, but also after the talk, we'll have just an unrecorded session where we can ask Renato further questions on the talk. So Renato, I guess I'll have one question. Maybe can you say a little bit more on exactly where the fact that you have this very fast convergence to the limiting monotone function comes in?
Mhm. Yeah, definitely. That was definitely not super explicit here. So the point is the following. Our first step was to get this inequality for Wasserstein distance. And then this Benamou-Brenier formula here tells us that if I give it any velocity field vt, so vt is going to be for each time t is going to be a map that tells me the velocity at all points in space. So it's again this two-dimensional map. And then it's telling me to integrate this velocity at all times and then integrate so over space and then integrate over time. So this is total kinetic energy. And if I can prove that that is small and takes me from my initial measure to my final measure, then the Wasserstein distance is small. So that's what the formula says.
Okay.
And then I hand wavily argued here that this integral of the velocity is essentially the same as this Dirichlet energy because I'm basically making equivalence between velocity and momentum. It turns out that this works up to some constant factor for our setting. So the point is that at the time zero, this integral here will be essentially equivalent to my energy functional, which is integrating these derivatives. So that's good. But to argue that the Wasserstein distance is small, I need to argue that the not only at time zero is its right hand side small, but when I integrate over all time is going to be small. But since I
Okay.
showed that this decays exponentially, it's dominated by the initial value.
I see. Okay. Um, okay, interesting.
Yeah, so the initial violation suffices to bound the total work that is going to be performed to reach the equilibrium.
I see. So that's why you don't, okay. That's why it only suffices to look at the violations at time zero, which is exactly the directional derivatives. Okay.
Exactly, yeah. Yeah.
Okay, cool. Are there any other questions? If not, I can take us to the unrecorded session and thanks everyone.